All right, let's dive in. We're going to go on a little journey today, one that starts right back in your high school math class, but it's going to end up spanning the entire globe. We're talking about geometry. And believe me, we're about to unlock some of its hidden power. So think about this. How on earth can a formula you learned for flat triangles, on a piece of paper, actually be used to measure the curve of our planet? I mean, it sounds kind of impossible, right? But the answer? Well, it connects some really beautiful ideas in a way you probably won't see coming. Okay, check this out. What you're looking at is a triangle. But this isn't just any triangle. It connects the North Pole, Boston, and Addis Ababa in Ethiopia. Its sides aren't straight lines at all. They're these massive sweeping arcs on a sphere. So how in the world do you even begin to solve a problem like that? Well, to get there, we have to start with something much, much simpler. So before we can start navigating the entire globe, we've got to go back, way back to the beginning. Let's revisit those first triangles we all learned about, and, more importantly, the one big problem they have. You remember your old friends, right? Pythagoras and SOHCAHTOA? They're great, they're fantastic tools, but they have one critical weakness. They only work if you have a perfect 90-degree angle. The second your triangle doesn't have one, which, let's be honest, is most of them in the real world, these tools are totally useless. So clearly, we need something more powerful, more universal. And that brings us to our universal toolkit. Meet the big guns, two absolutely brilliant laws that can handle any triangle you can throw at them, whether it has a right angle or not. Okay, so on one side, you've got the law of cosines. The easiest way to think about this one is like Pythagoras on steroids. It's your go-to when you know two sides and the angle that's squeezed right between them, or if you happen to know all three sides. Then, on the other side, you've got the law of sines. This one's perfect when you know more about the angles, say you know two angles and any one side. Look, the key here isn't to memorize the formulas. It's all about knowing which tool to grab for which job. Let's try a quick one. Take a look at this triangle. You've got two angles and one side length. So which one do you use? Well, since you're heavy on angle information, the law of sines is the perfect tool for the job. You've got just what you need to solve it. Okay, but what about this one? Here you know two sides and the angle that's locked right in between them. This is a textbook case for the law of cosines. And what's really, really cool about this particular law is that it's hiding a massive secret. All right, and this is where we take our first big zoom out. It turns out this simple little rule for triangles is actually a secret doorway into a completely different part of math. Yeah, it's so much more than just a way to find this side of a triangle. It's actually a fundamental principle of how vectors, things with direction and magnitude, interact in space. And the crazy part is, it's been hiding in plain sight this whole time. So to get this, we have to talk about something called the dot product. Now remember, a vector is just a thing that has both a size and a direction. Think of a force or the wind or your velocity. The dot product is just a specific way of multiplying two of these vectors together. And if you look at the definition, hey, there's that familiar cosine term again. Trust me, that is not a coincidence. So here's the thought experiment. What if the sides of our triangle aren't just lines, but they're actually vectors? Let's call them vector A and vector B. That means the third side, vector C, is just what you get when you subtract B from A. Now, here's the magic. If you calculate the length of that third side, C, and you square it, using the rules of the dot product, the math just simplifies and out pops the law of cosines. I mean, how cool is that? It's not just some random rule somebody made up for geometry. It's a direct, natural consequence of how vectors work. Okay, so we've built a bridge from geometry to vectors. Pretty cool. But now it's time for our second, even bigger zoom out. We're about to challenge the very paper our triangle is drawn on. Think about it. Everything we've talked about so far, Pythagoras, the laws of sines and cosines, even that cool vector proof, it all assumes one thing, that we're working on a flat surface, a perfectly flat plane. But our planet isn't flat. So what happens to all our nice, neat rules when we try to draw a triangle on a curved surface, like a sphere? Well, as you might guess, on a sphere, the rules have to change. This right here is the spherical law of cosines. Now, it looks kind of similar, but you've got to notice the crucial difference. The sides of the triangle, A, B, and C, they're now inside the trig functions. And why is that? It's because on a sphere, the sides of a triangle are really arcs, and we measure the length of an arc by the angle it makes from the center of the sphere. So it looks like we've got two completely different laws, right? One for flat planes and one for spheres. Or do we? This, my friends, is the moment where it all clicks into place. So how in the world do these two laws connect? Okay, just follow the logic here. Imagine you're on a sphere, but it has a huge radius, we'll call it r, so big that the sides of your little triangle are just tiny little arcs. And that means they correspond to really, really small angles. Now, there's a neat little math trick, it's a bit of calculus, that lets us approximate the cosine of these tiny angles. So we take that approximation and we plug it back into our big spherical law. And then comes the final step. We imagine that radius r getting bigger and bigger and bigger until it's basically infinite. And what happens when a sphere's radius is infinite? It becomes a flat plane. And as that happens, all the math just simplifies. And what are we left with? The good old standard flat plane law of cosines. This is the big reveal. The flat law isn't a different rule. It's just a special case. It's what you get from the more fundamental spherical law when the curve is almost zero. And I promise you, this isn't just some cool mathematical party trick. This idea is the absolute bedrock of how we navigate our world. We're talking aviation, shipping, mapping, all of it. So let's go all the way back to that first problem, finding the shortest distance between Boston and Addis Ababa. To do it, we make a triangle connecting them to the North Pole. Because we know the latitude and longitude of both cities, we can figure out the lengths of two of those arc sides, and we can also figure out the angle between them at the pole. And just like that, we have everything we need to solve it. You just plug those numbers into the spherical law of cosines, solve for that third side, and boom, there's our answer. The shortest path, the great circle distance, is about 10,900 kilometers. A problem that seemed completely impossible is solved, all thanks to a formula that describes the fundamental geometry of our world. So, let's recap what we've just figured out. We've seen that a basic rule for triangles has these incredibly deep connections to a whole other field of math, vectors. We've learned that the law of cosines is this beautiful bridge connecting geometry and algebra. And maybe the biggest takeaway of all is that the flat, simple geometry we learn in school is really just a special case of the more general, curved reality we actually live in. And that just leaves us with one final thought to chew on. It really makes you wonder, doesn't it? What other rules that we take for granted every day are really just shadows, simplified versions of a much bigger, more elegant picture that's just waiting out there for us to find? Thanks for coming along on this one.